Welcome to video 13.1 in our first Principles of Astrophotography series. In this video, we explore the conditions under which sensor images capture all possible detail in the sky without wasting pixels.
We talk about critically sampled, well-sampled, undersampled, and oversampled images. Undersampling isn't bad, and drizzling can be used to recover details in undersampled images.
This video is based on section 13.1 of our First Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. 137, sampling. This is actually kind of a hard topic for me because it seems opposite. To sample is to convert a continuous image into an array of discrete pixel values.
So if you have in one dimension, let's say you're measuring pressure versus time in a pressure wave. When we're speaking, we're creating a pressure wave that's high pressure, low pressure as a function of time. This may seem irrelevant, but it is relevant.
It feels irrelevant.
What you're doing is you're discretizing the time, and you're taking particular values at each time.
Okay.
That's what sampling means. And so in an image, you have a picture of a mountaintop and a beautiful lake, etc. Then you're discretizing this way, and you're taking that continuous image of the mountain, creating individual discrete pixels, measurements,
right,
colors. This is an image of an amazing part of the sky where we happen to find 9 exactly identical stars matched up.
I think this is actually, this is in the Bermuda Triangle or something.
Oh,
or
the Bermuda Triangle. Pickering's Triangle, Pickering's Triangle.
But you can't see this specific part of the sky, though.
So anyway, this is a manufactured picture of 9 stars arranged in a rectangular grid. And we're pretending that these stars are separated by the full width at half max of their star profiles. We're using this ugly looking circle with a little H in the middle of it. It's called theta. It's capital theta. And this I stands for half intensity. And we talked about this in a previous video, but basically, if you look at the intensity of the star as a function of angle, then this would be the maximum intensity, and here would be the half maximum intensity.
Yeah.
And then this width right here between these 2 points is the full width at half max.
I don't understand why they say full, because it's just the width at half max.
Yeah, you can also talk about the half width at half max, which is this distance right here.
Oh, sure. Okay, I'll get it.
So
full.
this is the full width at half max and the half width at half max.
Fair.
That means if you take 2 stars and you separate them by that by that full width at half max, the same distance separating the stars as is the width, then you can, like we talked about in a previous video, you can barely distinguish those stars. This is essentially the Dawes criterion that we talked about before. If you're looking at 2 stars that are separated by that amount, these blobs are going to be much more spread out, and you're not going to see as much black on here. But I've exaggerated it just so that we can see what we're doing here. So this blue distance, this double-sided blue arrow, is the distance between those stars, the angular distance, and this is measured generally in arc seconds. Now, the question becomes, in sampling this group of highly idealized stars, is to ask the question, how many pixels do I need to resolve all of those 9 stars? And the answer is, if I have a pixel size that's this size, that's my pixel size, then that pixel right here is going to have the same amount of light hitting it as this pixel right here. And you're not going to resolve them.
No.
So you need a pixel between the two star centers in order to resolve them. That's called the Nyquist criterion, or the Nyquist limit. So you say, no, I want more than that. So let me have a pixel that's centered on this bright star here, a pixel that's centered on this bright star here, and a pixel between them in the dark region between the two. And if I have that extra pixel between them, then I can say, oh, this pixel is bright, and this pixel is dark, and this pixel is bright, and I can tell that there are two stars there.
It's almost a I/O thing. It's almost a 1 or a 0.
Yeah.
But it's not. It's there. We're picking up brightnesses on pixels, not just whether it has something or not. But yeah.
That's right. And so if your camera sensor happens to be oriented exactly the right way for this purely hypothetical Bermuda Triangle situation, then you can resolve these with a pixel. So this green arrow represents the pixel scale. It's the number of arc seconds per pixel, which you can calculate using the formula that we derived earlier. But if this pixel scale, that's the pixel, and this is the full width at half max. If that pixel scale is half the full width at half max, full width at half max is this blue arrow, pixel scale is half of that, then you should be able to resolve those stars if they're lined up in this perfect way. So, well, stars don't always align right along the line of your X and Y axes of your sensor. Sorry. Sometimes they're aligned in weird ways. And so what happens if they're aligned diagonally like this? So this full width at half max, this blue arrow, is the same length as it was before. We're talking about the same group of stars, but now we're just rotating the camera or rotating the stars.
Maybe we're on an altazimuth. Yeah.
Maybe we're on an altazimuth. Yeah, very good. And now we're in the unfortunate situation where these stars are lined up diagonally on the grid. What size, what pixel scale do we need? And the answer is right here, and we're about to derive it. So between this pixel, this one right here, and this one right here, I definitely need, so both of those would be bright pixels, right? And we need one dark pixel between them, which basically means that I need here's 1 pixel width, here's 2, so this distance is 2 times the pixel scale, because remember the pixel scale is the number of arc seconds per pixel. Each one of those red rectangles represents a pixel. And then I also need from here to here 1, and then from here to here 2. So that distance measured in angle is twice the pixel scale. And now, since this hypotenuse is the full width at half max, that's the full width at half max, which we represent as theta I, we've now got a triangle. A right triangle. This side is 2p, this side is 2p, this side is theta, and a squared plus b squared
Equals c squared.
equals c squared.
Yeah.
So a is 2p plus b is 2p equals theta I squared, and that's c squared. So let's do the math. It's not hard. In this first term, we have 2 squared, which is 4, and then we have p squared. So that'll give me 4p squared plus 4p squared equals theta I squared. Well, we have 4p squared plus 4p squared. That's just 8p squared. We just add 2 terms up.
Could you take the square root?
And we're going to take the square root.
Nice.
case. So we take the square root of 8, which is square root of 2 times 4. Pretty sure I learned that in the 3rd grade.
Yeah,
2
nice.
times 4 equals 8.
Yeah.
Square root of p squared gives me p.
Yeah.
Square root of theta I squared gives me theta I. And now, the square root of 2 times the square root of 4, well, the square root of 4 is something we already know about. That's 2.
I love that one.
You love that one. And the square root of 2 is an ugly number,
Yeah.
1.414. So basically we found that theta I is 2 times the square root of 2 times p. Or, if you divide both sides by 2 square root of 2, these cancel here, and p equals theta I divided by 2 square root of 2. That's the algebra. What does it actually mean? Well, remember, to just resolve, in this case, we needed a p that's theta I divided by 2.
Mm-hmm.
Now we need a p in order to resolve these stars that are diagonally oriented with respect to the camera sensor array. We need theta I divided by 2 divided by the square root of 2, which is roughly theta I divided by 3, roughly. So you need a smaller pixel scale to resolve those diagonally oriented stars.
Pesky diagonals. Okay.
Yeah. But this, if your pixel scale is that, then you're going to be able to resolve any orientation, because, I mean, we started off with stars oriented like this, then we rotated this one up to here. Well, if we rotate it over here, we're back to where we started again.
Right.
It's just still the same, it's just rotated.
Yeah.
So the worst case scenario is this 45-degree
Yeah, we're hitting
rotation.
the extremes.
We're hitting the extremes. So this is what's known as the critical pixel scale. Why is it called critical? It's called critical because for any star orientation, this pixel scale will resolve those stars.
All right. Principle 138, critically sampled. The critical pixel scale, well, the equation we just derived, just resolves all stars in an image where theta I is the full width to half max of the star profile.
So it just resolves, meaning it barely resolves. That's how I'm using that word.
Just.
It just barely resolves all stars in the image.
Well sampled, pixel scales p between theta I over 4 and theta I over 2 are well sampled, where theta I is the full width to half max of the star profile. Lower values are oversampled or too densely sampled. This is the part that sticks in my brain from all of this. Oversampled is too dense, and higher values are undersampled or too sparse or too far away.
So this is a mouthful. Why theta I over 4 and theta I over 2? So when we first started studying this, we found lots of different ranges for well sampled. And why would you want a range? Why don't you just want to shoot for the critically sampled? Well, all stars are not lined up in a nice grid.
Dang it.
All stars are not the same brightness, and so it makes it harder to resolve a smaller star compared to a brighter star, a dimmer star compared to a brighter star. And so people generally talk about a range of pixel scales that would be satisfactory for good sampling. And the other part of it is that generally you're not going to be able to find the exact right focal length you need and the exact pixel size to nail the critically sampled part.
Yeah.
There's just a lot of variables, so we like to talk about a range. So the way that this range, that we recommend for defining this range, is to take that critical pixel scale, multiply it by the square root of 2. So if you take that pixel scale theta I over 2 times the square root of 2, and you multiply it by the square root of 2, then the square root of 2's cancel, and you get theta I over 2. That's the upper limit. So this is the upper limit of the well sampled range. And then you divide that critical pixel scale by the square root of 2 to get the lower limit. So you say, all right, theta I over 2 square root of 2. Instead of multiplying it by the square root of 2, I'm going to divide. Well, what do you get then? Well, we still have theta I in the numerator. Then you have a 2 here. And you have a square root of 2 times the square root of 2. And that's kind of magical. Because the square root of 2 times the square root of 2. So it's 2. This is the lower limit of the well-sampled range. That's this bad boy right here. Let's do a couple of examples. All right, let's say we have 2 arc-second seeing. It's pretty typical. So that means that theta I is 2 arc-seconds. It's not great, but it's not terrible, right? And let's say we have William Optics Cat 91 that has an ASI 6200mm Pro. That camera has a pixel size of 3.76 microns. This is one of the telescopes that we owned until very recently. And then the focal length of that telescope is 448 millimeters. The units work out so that you get 1.73 arc seconds per pixel. So this is always your starting point in determining whether you're undersampled, oversampled, etc., etc. Figure out your pixel scale for your telescope camera combination. And then your next step is to say, what's my seeing? And a lot of times we don't even know.
Yeah.
There are ways you can measure it. You can measure the size of the volts at half max, but
You can look at astrospheric.
you can look at astrophotographers, which gives a prediction of what you're seeing is going to be on a particular night. But there's also wind that causes things to jiggle around. Anyway, so you can just say, all right, let's say I've got 2 arc-second seeing. If you're on the top of Mauna Kea, the telescope in Hawaii, then your seeing is going to be 0.5 arc-seconds, whatever.
Great.
Merry Christmas and happy news for you. Yeah, good for you. So let's just say we've got 2 arc-second seeing, and you can do this calculation with whatever you figure your seeing is. Then theta I over 4, the lower limit, is 2 arc-seconds divided by 4. And 2 over 4 is our old friend 1/2.
I could have done that one.
You could have. Yeah,
Yeah.
you sure could have.
Square roots mess me up.
So that's the lower limit for the well-sampled range. That's this limit right here. Then the upper limit, theta I over 2, is 2 arc-seconds divided by 2. And 2 divided by 2 is our old friend
That I know, 1.
7.
What?
Right. 1 arc-second is
I
upper
was
limit.
right.
If P is between 0.5 and 1, we're well sampled. Well, what's P? It's 1.73. So are we well sampled? Is this number between these two numbers?
No.
No, it's not, and that's very embarrassing.
This is where the flip comes in, though.
This is where the flip comes in. So we want to be measuring, so if we're measuring off, it says 0, 1 arc-second, 2 arc-seconds, etc., then our lower limit would be a pixel size that's half an arc-second. That would be our lower limit pixel size. And our upper limit pixel size would be
1
here.
Yeah.
But our pixel scale is not pixel size, but pixel scale is what I meant. Is 1.73, so it's not 1.5 here, about there. So this is our
So we're taking more of the sky than our camera combination. Our camera combination is capable of taking less sky than we're taking.
That's right. So this is our upper limit, which is 1, and here's our lower limit of 0.5. So lower values are oversampled. In this case, a higher value, this value here is higher than this range. So we're definitely in this camp here, right? 1.73 is bigger than 0.5 and bigger than 1.
Yep.
We're undersampled. We're too sparsely sampled.
Right.
We're leaving some detail on the table.
We need more pixels.
We need more pixels. Or we need to dither, which we'll talk about in a future video.
Drizzle.
And drizzle. Dither and drizzle. That's a good example of being undersampled. Your pixel scale is too big to capture all of the possible detail in the image. All right, let's take another example. Celestron EdgeHD 9.25.
Same 2 arc-second seeing.
Same seeing, different telescope, same camera. So the camera pixel size is the same, but now the focal length is huge.
Yeah.
And we're dividing by the focal length, and that gives us a pixel scale of 0.33.
This is embarrassing.
So the embarrassing situation is with this seeing, again, we're talking about 0.5 arc seconds up to 1 arc second, because I'm just taking this 2 divided by 4 and 2 divided by 2 to get these numbers for well sampled. Now, do bigger gradations here. Here's 0.
We need a 0.5.
Here's 1. Here's 2. So we need 0.5.
Well, we don't need to go up to 2.
No, we don't. And here's our 1. And now our pixel scale is 0.33. So it's not, there's a half. So we're really talking about something that's about this size. This is our well-sampled range. We're below that range. We're taking too many samples. We're oversampling.
So our camera and telescope combination can't resolve that amount of detail that we're trying to get from each pixel.
That's right. Yeah, and so is it bad? Well, not really, but
there's nothing you can do to fix it. You can't dither or drizzle it.
No, you're dead. You're just not going to be able to. You're basically wasting pixels, and that's not bad. I mean, you just process it and whatever. But so that's the case where we're lower values than this well-sampled range are oversampled, too densely sampled, and that's sampling. Thank you so much for watching.
Yeah, we'll see you next time.